This video shows how to program Arduino the modern way. With the QP real-time embedded frameworks, hierarchical state machines, graphical modeling, and automatic code generation. I'll start with downloading and installing the QP Arduino software. Next, I'll explain the directories and files comprising the installation. And finally, I'll give you a quick tour of the features. So, starting with downloading and installation. Point your browser to statemachine.com/Arduino and scroll down to the downloading section. Here you can find downloads for Windows, Linux, and Mac OS computers, as well as a link to the GitHub repository. Choose the download for your host operating system, which is Windows for this video. The downloads contain the QP C++ and QP Nano frameworks packaged as Arduino libraries, and the QM modeling tool bundled together in a single zip file. Now, regarding the installation, I assume that you already have the standard Arduino IDE installed on your machine. So, please open it up and go to File, Preferences menu. Here, select and copy the sketchbook location into the clipboard. The sketchbook lives typically in your Documents/Arduino folder. As you are at it, also check the Use External Editor box, because you will edit your Arduino code externally. Now, extract the QP Arduino, zip it to your Arduino sketchbook folder. Let's now take a quick look at the main directories and files that have been installed. The first directory inside your Arduino sketchbook contains the libraries. These are the QP C++ library for the SAM-based Arduinos, that is, Arduino boards with the 32-bit ARM Cortex-M processor. And the QP Nano library for the AVR-based Arduinos, that is, Arduino board with the 8-bit AVR Mega processor. The support for the older 8-bit processors and QP Nano will be discontinued in the future, so this library is only intended for backwards compatibility before you switch to the more contemporary boards. By being located in your Arduino folder, the QP C++ and QP Nano libraries will be visible to all your Arduino projects located anywhere on your disk, not just in your Arduino sketchbook. Apart from these libraries, you also get here the QM modeling tool, which will be your visual external editor. To make the tool more accessible, you might want to get into the QM bin directory, right-click on qm.exe to open the pop-up menu and choose the Send to Desktop option to create a desktop shortcut. Now, let me give you a quick tour of the examples and other features. I'll start with the examples for SAM-based Arduinos, located in USketchbook, Libraries, QP C++ SAM, Examples. The first here is the simple Blinky project, that blinks an LED on the Arduino DO board once per second. First, open the QM model for this project blinky.qm. Right-click on this file and choose the Open with Pop-up menu option and select the Choose Another App option. Now, find the qm.exe application and also check the box Always use this app to open .qm files. This opens the blinky.qm model in the QM tool. This model is for a simple Blinky for the Arduino DO board. It demonstrates one active object, a simple state machine, and all code located in one blinky.eno file. Let me quickly review this Arduino sketch. It starts with including the qpcpp.hpp header file for the QP C++ framework. Next, you can see the highlighted $declare directive, which tells QM to generate the declaration of the Blinky active object in this place in the code. Next, you can recognize the usual Arduino setup function, which initializes the framework and then it configures the pin for built-in LED as an output. And finally, the setup function starts the Blinky active object with a given priority and event queue buffer. The Arduino loop function calls transfers control to the framework to run the application. Below this, you can see code related to interrupts, because the QP applications are interrupt-driven. So, here is the code to handle the time tick interrupt, to configure the timer for the tick interrupt, and to enable the interrupt. Below this, you can see code to handle the idle condition, where the system is put to sleep to save power. Below this, you can see code to handle assertion failures. And finally, you can see the $declare and $define directives, which tell QM to generate declarations and definitions of the specified model elements. You can use the provided blinky.eno sketch file as a starting point for your own projects, so you actually need to change only the Arduino startup function to configure the hardware and start your active objects. Alright, so now, let the QM tool generate the code, which you can very easily do by clicking the Build Code button or by pressing the F7 shortcut key. This generates the complete blinky.eno file on disk, based on the blinky.eno file template in your model. The file is always regenerated, but it is replaced on disk only when there are differences. Now, when you compare the file template in QM and the generated file on disk, you can see that the file on disk has all your code literally copied over, but all $declare and $define directives are now replaced with the generated code. This makes it very easy to mix handwritten code with auto-generated code. So, the last step is to build the generated code and load it to your Arduino Uno board. For this part, you will use the standard Arduino IDE. Please note that you should not edit the generated code in the IDE anymore. That's why you configured the IDE to use an external editor, which is QM in this case. At this point, you can connect the Arduino Do board to the USB port on your PC. After this, you just press the Build and Upload button on the Arduino IDE. After the build and load completes, you can see that the built-in LED blinks about once per second. But at this point, the main question you might have is, why should you bother with all this? I mean, the Blinky application developed in QM is far more complicated than the standard Arduino Blink example. The traditional Arduino programming model is called sequential programming, because you hard-code the expected sequence of events and the sequence of blocking calls in which you wait, in line, for the expected events to arrive. For instance, in the standard Blink example, you expect the timeout events for which you wait in line by calling the Arduino delay function. The main problem is that your program cannot do anything else while waiting. Such approach works for simple problems, but scales poorly and quickly becomes expensive for more complex projects, where you need to many things simultaneously, like for instance to blink a second LED at a different rate. In contrast, the event-driven approach scales much better, so even though it is obviously more expensive for toy projects like the Blinky, it is much more cost-effective as the complexity of your projects increase. This is because you never wait for events inline, so your software remains responsive to any new events. You can think of the QP framework as an operating system, or more precisely, a real-time kernel, that can manage many active objects simultaneously and can easily handle thousands of events per second, not just 2 timeout events per second like in the simplistic Blinky example. So, for instance, to blink a second LED, you can simply add another Blinky active object that would do this for you. In fact, exactly this is demonstrated in the Blinky 2 example, which you can open in the QM modeling tool. You can edit the model and generate code. Now, you can open the generated Eno file in the Arduino IDE. But before you build and load the Blinky 2 code to your Arduino Do board, you need to connect a second LED to pin 12. On a 3.3-volt board, like the Do, you can simply insert a green LED directly to the board without a limiting resistor. You only need to remember to put the shorter leg of the LED to the ground. This would not work for a 5-volt board, like Arduino Uno, so please be careful. When you finish building and loading the code to the board, you can see that both LEDs blink simultaneously, but with different rates. Another example that shows multiple active objects is the classic dining philosopher's problem (DPP) application. Here you simulate 5 philosophers sitting around a table with 5 forks between the philosophers. All philosophers are active objects, and the table is also an active object. The details of this application are described in the application note, which is included with the example. This example also demonstrates an Arduino project with multiple .cpp files and the concept of a board support package to access the hardware through a well-defined interface. As usual, you use the QM tool to work on your state machines and also to write any code you need. Then you generate the code and use the Arduino IDE only to build and load the binary image to your board. For the DPP application, the additional feature is the use of the serial terminal from the Arduino IDE. You can watch the changing status of the dining philosophers, and you can also pause the serving of forks with a P key press, and resume serving the forks again by pressing the S key. This concludes this quick introduction to modern Arduino programming with QP and QM. To learn more, please visit statemachine.com/Arduino. Thanks for watching.